Dear colleagues, students, and fellow ISE participants, I want to now make a presentation about my research and my paper on earthquake detection and disaster forecasting with University Cubesats. As you're aware, earthquakes are a very critical phenomenon that causes a lot of financial damage as well as a loss of a large amount of human lives all across the world, especially in certain locations where there's a lot of seismic activity. If we look at the mortal damage caused by earthquakes, we can see over the decades that in spite of the advancing technology, in spite of advancing civil engineering technology, still a lot of people have been dying across the world because of earthquakes. And though we have means now of perhaps detecting earthquakes a few seconds before they happen, the importance of forecasting an earthquake perhaps a couple of hours before it happens, or maybe even a day before it happens, would be a huge win for science and technology and for humanity, because then we can give this certain warning to people and say that you need to evacuate your homes because this scale earthquake, let's say magnitude of 6 or 7, is weighted in your area within the next couple of hours, so you must evacuate at once. That can save all the lives that may be lost. That can save all the injured that may face mortal injuries. So the ability to predict an earthquake before it happens is more important than ever. So what are some of the interesting earthquake precursors before an earthquake? We know through various research, experiments, theory, that before a major earthquake happens, certain anomalies also takes place. One of these important anomalies that scientists have been working on is that they've been able to demonstrate in a laboratory that when you put rocks under extreme pressure, which earthquake also creates, you're able to create electric charge inside the rocks. The heavy pressure on the rocks, creating stress on pulling direction, would actually create electrical charge, and that electrical charge disperses through the ground, creates ionized gas, and then this ionized gas, or ionization rather, is detectable if you have the right amount of equipment looking at the right place. So these ionized gases escaping from Earth's crust into atmosphere, not only from rocks but from other sources as well, would be causing electromagnetic field fluctuations that may be detected from low Earth orbit. So when we say low Earth orbit, what do we mean? We mean roughly anything between 500 kilometers of altitude to 1,000 kilometers of altitude. That's the definition of a low orbit. Technically, low orbit starts at 100 kilometers. So if we can detect these changes in the electromagnetic field at the upper atmosphere, if you can detect these ionospheric responses before an earthquake happens, then we might be able to say that if we see a certain degree of fluctuation at this particular frequency in the atmosphere at this particular range, then this signals that there may be an important seismic event happening in that source region, if you think of it as a cone. So roughly, if we have means to detect these at the upper atmosphere, then we can plot their origin. Okay, so we can create a cone where on the ground there's an origin where these ionization precursors are taking place and affecting a region at a top altitude. So by matching these to existing seismic activity, we may be able to understand that a certain seismic event is about to take place. Obviously, you would need more than one nanosatellite at various dispersion points to create a good coverage of potential zones, because you want to make sure that you're able to catch all these fluctuations in a zone of coverage. So potential zones like Nepal, California, Japan could easily be checked using this method. So here's an interesting diagram. The one on the right shows disturbances in the ionosphere after the Nepal earthquake. So you can see on the right that the Nepal earthquake has been creating an ionospheric effect. Of course, the important thing that we want to do is we want to be able to detect before the earthquake itself. So as you can see on the left, these perturbations can be detected at the VLF UHF level. So if we have the right amount of CubeSats, I would suggest about at least 7 on a particular region to create full coverage. Having scanners, especially in the Alpha range, then this would go a long way in predicting earthquake. Of course, we have to take a lot of data and we have to superimpose this data on actual seismic data to see how this atmospheric data corresponds with seismic data to see these precursors and create an algorithm for predicting earthquakes. And I hope that with the right amount of budget in the future, universities will be able to do this easily. Thank you very much for listening to my lecture. My website is drgrant.com or www.aerospacelectures.com, both of my websites. Please feel free to contact me on this particular issue or any other issue. Thank you and enjoy the rest of ISC.